You're live.
All right, thanks everyone for joining us today on another SparkFun Education. We have with us today Nick Provenzano, also known by his handle, The Nerdy Teacher. Nick taught high school English, and he is now the Technology Coordinator and Makerspace Director at University Liggett School in Michigan. He shares his thoughts on education and technology on his site, thenerdyteacher.com. I recommend everybody check that one out. He has been featured on CNN, Education Week, the New York Times, and he works closely with educators around the world to help promote maker education. His best-selling book, Your Starter Guide to Makerspaces, is available online. Welcome, Nick. Thank you for joining us. So can you tell us a bit about your background as a maker? How did you get introduced to the maker movement?
I think, like all of us, I was a maker since birth. I think all children are natural makers. They are constantly exploring their environment and doing whatever they can to alter it to meet their needs. So from there, I've always been a person who has been a tinkerer. Best example is when I was younger, my parents lived in this house that had this like walk-in safe, which is super crazy. But when we had the house, it didn't have a combination, so it's stuck in the locked position. You can still open it, just you wouldn't be able to lock it. I was determined to figure out the combination to this safe, and so I did some research and learned how to take it apart, find the combination, put it back together, and to test it, I left my little brother in it, and it was a success. So that's one of my earliest like maker memories of just like wanting to know how something worked. And so I took it apart to figure it out. And I think that's one of the hallmarks of that. And as a teacher, as a former English teacher, I was a big advocate until I am of project-based learning. And so making falls right into project-based learning where kids can explore different avenues to demonstrate understanding. And so having a makerspace was a very natural connection for me, which is why I put together one in my high school, and now I'm putting one together in the middle school I'm at right now.
Question for you about going back to the safe. One, was your brother upset? That's hilarious, by the way.
Oh, he was very upset. Mom was very upset. Dad had to pretend to be upset, but he was very proud of the fact that I figured it out. It was one of those, like, you should have done that, but wow, I'm really impressed that you figured that out. But, you know, it was a sacrifice for science, I'd say, my grounding for the week.
Right, that's for sure. Did your parents continue to encourage things like taking things apart and making, or was it kind of discouraging you continued it on your own?
My dad always was a tinkerer too, which was crazy. As I think about it now, he would always have a soldering iron on his desk. And I would see him doing things. This day, I can't remember exactly what, but he had his workspace downstairs where, you know, hammers and nails and building things. And so he was always making stuff with his hands. My mom would like paint and clean up the things. It was surreal as I look back on it now, how much that impacted me wanting to build things and make things with my hands. And my dad's a doctor, so it's not like, you know, it was his like initial trade, was, you know, carpentry. He just loved to do that, and it helped him think. And he relaxed by like making and tinkering things, which is nuts because of how busy he was. You think he just wanted to lay on a couch and sleep, but he would tinker. So I kind of do the same thing, is that to help me think about other things, sometimes I'm just making something else and it kind of clears my brain. It's super weird.
Right, just doing something with your hands kind of puts you in that Zen mode and takes you away from the world for a little while. Other than your dad, who else do you consider a role model in this makerspace? I mean, you can go back, you know, several hundred years if you want, but who do you look up to when you say, you know, that person was awesome and I want to be like them?
I'm a huge history guy too. I'm certified in English and social studies history. I look at someone like Leonardo Da Vinci. When you talk about like makers, my son is named Leonardo, so I can throw that out there. Because this is a man that's like, hey, I don't know how this would work, but I'm going to invent a submarine, or I'm going to invent a helicopter. Like, this is a man hundreds of years ago that was exploring all of these things. It was exploring some things that, you know, socially he wasn't supposed to be exploring, whether it was anatomy and things like that. I mean, this is a man that at times risked his well-being to explore ideas that everyone said is not possible. So you look at someone like Da Vinci is huge to me as someone that really set this bar, or, you know, you fast forward someone like Ben Franklin. Ben Franklin was a maker. Thomas Jefferson was a maker. We talk about Thomas Jefferson, but like he invented a lot of things. You know, we don't talk about some of those things. So even some of our early founding fathers were inventors and makers and hackers, we would say, trying to just improve upon things because they had to. They were living in a world that was probably going to try to kill them any minute, whether it was the wilderness, disease. These were people that needed to hack their surroundings and make things to make it accessible. So you look at that, you know, as a country, we are founded by makers trying to alter their surroundings to get the most out of it.
And do you see a lot of that coming out of necessity, like they made because it was necessary, or was it a curiosity and a fun pastime for them?
I think for some, it was definitely a fun pastime, but for others, it was a necessity. As the U.S. expanded west, I mean, there were inventions to make that possible, or the need to go across the country, or the need to travel better than horse and carriage. So I'm in Detroit, so you think of Henry Ford, you think of the car, you think of the assembly line. I mean, these are massive innovations that were part, you know, necessity. Like, hey, I don't want to get someplace without having to take care of a horse all the time. Like, those are things that we take for granted, but someone had to sit and think about that. Someone said, you know, this assembly line, I want to make things faster and more efficiently. So, you know, those were taking things that existed and tweaking them and hacking them and making them what they are. So for me, being from Detroit, you know, that's a major part of our history is innovation and making and really creating what we need to really go to the next century, whatever that might be.
Yeah, and that brings it back to the classroom where we see students today. When I was in school, what was that, back in the late 90s, early 2000s, there was no shop class anymore. They didn't teach us how to use lathes, mills, and make, really. We had a computer lab, and that was kind of it. So this new idea of makerspaces is here, and can you tell us about your makerspace? Because you wrote this book, your starter guide to makerspaces. What does yours look like? What does your makerspace look like?
So my makerspace is constantly evolving based on the wants and needs of the students, and that's definitely something I want to share out there. Is that while my space has 3D printers, it has CNC mills, it has a laser cutter, I'm also stacked to the roof with cardboard. I have a group of students that are just dedicated to building a cardboard fort and come down. I've had to order twice as much duct tape because they're duct taping everything together, and cardboard, house and roof, and they've added shelves. And one kid said, "Oh, you're probably thinking this is crazy that we're not using any of the technology." And I go, "No, this is awesome. This space is for you." I have these tools based on other students who have needed to do certain things for the theater program or for social studies class. But if you guys need cardboard, I will go out and get you all the cardboard in the world. If you guys need more duct tape, I'll get you the more duct tape. So my space is constantly evolving. At the start of the year, it was a lot of coding. There was a lot of kids using Raspberry Pi and doing physical computing, making LEDs, motion sensors, buzzers go off, because that's where the kids were. And then it shifted, and kids were like, I really want to start doing more physical things. So watching them employ geometry and watching them employ sort of physics to a degree as they understand how to build certain things and as they plan. And really it's the design process that I think is most important as they're building with cardboard. So some teachers say, well, what's cardboard have to do with STEM, or how is that important? It's the process. It's the idea of having an idea, designing, trying it out, going back to the start if it doesn't work. That ideation aspect of learning is key, and watching sixth graders do this is key, because those are skills that'll help them as they advance through 7th, 8th, 9th, 10th. As they encounter problems, they'll have the skills to walk through solving that problem. So my makerspace is awesome, and it's really focused on what students want and what students need. And my job is in a service position to help them get the things that they need and point them in the right direction of resources that might help whatever it is that they want to do.
That's pretty cool. Do you find that the students will often, once they come in, are they a little timid at first to play with this stuff? And do you find they gain more confidence as they use the tools and become less afraid to ask questions and try new things? Because that's when I started making and doing things with my hands. I'm a classically trained engineer, which means I was perfectly comfortable solving equations on a piece of graph paper. But when it came to actually building and soldering, I didn't have much skills. When I got into this, I started building things and I became more confident of like, you know what, let's just try it. That's my personal experience. What do you see with the students?
It's always better for them if they have a friend that invites them in. It's very tough to come into a space sort of solo and just trying to figure it out. So that's okay because making is, in my opinion, a communal effort. Makerspaces need to be community spaces. Makers, by their nature, tend to be rather communal in the sense that even online communities like GitHub. I remember the first time I posted code that I wrote on GitHub. For those of you that don't know what GitHub is, it's an online website that stores code from coders from all over the world. And so it's this repository where you can go and snag lines of code so you don't have to reinvent the wheel. So I uploaded this code after reaching out to some people who wrote different code and saying, hey, can you help me with this? And people from all over the world were like responding. This guy from France was helping me write my code. And so when I uploaded my first set of code, I felt like a real coder. I'm like, I'm an official coder. I was so excited. And so my students are experiencing the same thing when they come into this space and they start just connecting with other people. And I had this 6th grade girl help this 8th grade boy with his code he was struggling with. And I was like, nowhere where you would ever see an 8th grade boy let a 6th grade girl help him with his like homework. But this was something she knew and he didn't. He's like, yeah, help me. Like, I just really want to know what it is. So the Makerspace creates this sort of even playing field for everyone based on what your skills are. So it doesn't matter if you're a 6th grader or an 8th grader or in high school. You know, making is about skills, and my Python skills used to be at the bottom of the barrel, and now they're maybe 2 notches above that. But that's because, you know, I reach out to people in the community, and if I forget something, I can send a tweet, I can reach out to friends that know the code, and that's what I want to emphasize in my space. Any makerspace is that this is a communal effort for everyone to get together and share and grow and support one another. So as you see projects evolve over the years, you're going to see people interact with others and pick up bits of information. I think that's how we become really well-rounded learners, whether it's STEM, STEAM, makerspaces or not. Being okay with learning from other people is how we can all grow.
So question for you around that. How do you help foster that in the makerspace? Some of the communities that I've had, especially these clubs, what'll end up happening is there's a few people who will get really good and they kind of form a clique and they don't turn around and help others. I've seen this time and time again, and it creates this sense of I don't belong here with some of the newer students, and it's kind of unfortunate to see. So what do you do in your makerspace to help foster this? Or do you find the students who come in are naturally self-selecting to want to volunteer and help others around?
Yeah, I found, and maybe it's because the age group, this middle school age group, which are still not quite jaded in regards to socially interacting or being good like team members, so to speak. These are kids that come in and have no problem, and my job is to sort of sit back, sometimes observe how the interaction's going, and maybe point someone's like, hey, so-and-so needs some help, can you give them a hand? And that all boils down to relationships I have with students, because they really look at the space as a really cool privilege to have, and my job is to maintain it and support them. So if I say, hey, will you help so-and-so? They go, okay, cool, like, yeah, I'll do that. And they'll go over there and they'll help, because they know that we're all sort of in this together. And so if one person struggles, that could lead to everyone struggling if they're working on one aspect of a larger project. I try not to have set projects to say, hey, welcome on Tuesday, here, everybody work on this. But if someone comes in and says, I don't know where to get started, sometimes I'll direct them to kids that are already working on a project, say, hey, go see what they're doing. Maybe you can help, or maybe it'll give you an inspiration for your own idea. Or I'll point them to some websites or I'll hand them a book. One of my favorites is the Great Big Book of Makerspace Projects by Colleen Graves. It is just a book filled with projects, and I love giving that to kids and saying, hey, find something. And no matter how tough it is, we'll see if we can put it together for supplies-wise, and you can get to work. So it's been very nice to see the kids just support each other naturally. And then if I need to give a nudge, I give a nudge, and the kids are totally accepting of that.
Sweet. So by the way, if anybody's curious, please feel free to ask us questions in the YouTube chat. We do have one already, or a few, around what does it take to bring some of these electronics into the classroom, specifically around science. So I know that you played with the microbit for a little bit. Can you give us examples of how you brought electronics into the classroom, say trying to merge this idea of a makerspace or the maker mentality into the classroom setting?
Yeah, so part of my job as a technology coordinator is to work with teachers to help them see or find some of the things that can enhance a learning experience that they just don't have the time to explore. You know, I was a classroom teacher 15 years. I know what it takes to just lesson plan and get through the day, on top of, you know, the hours I would put in looking to integrate certain things. So some teachers don't have that time, and, you know, part of the awesome position as technology coordinators to meet with them and see what they want to do and what's out there. So the microbit climbing kit is a wonderful example. So I started this new job this year, and so I got the climate kit over the summer, and I was like, ooh, this could be fun in a science class, because it can take wind speed, temperature, humidity. So I asked the science teachers, I said, do you guys do a climate unit? They said, yeah. I said, I have this kit that the kids can block code and it'll gather all this information. And they're like, that's amazing. So I showed up with the kit, walked all the kids through the coding as part of it, and they started to log information outside in regards to temperature and humidity. And so then the kids started to build the enclosure for them, because they're like, oh, this can't be out in the rain, what if it rains? And so the next thing, you have got kids exploring design to build a case for it. And then they're like, oh, a battery pack, we don't want to have this plugged in, so we need a battery pack. So watching the kids go from more than like just sort of discussing climate and smaller in-class examples with maybe a thermometer, to have the microbit and have the whole climate kit together was an extension for them. And one day we just walked around in different parts of the school and took temperature. That's one of the things that we did. So it would show up on the display, the kids would write it down, and they took guesses as to what parts of the school they thought would be colder as opposed to others. So, you know, they said, oh, the enclosed areas were not as cold as the ones that were outside. And it was just fun to see them sort of explore all these different aspects, because they were able to walk around with a little microbit and watch the temperature show up on the LEDs there. So that's just like one example of using the kit that I thought was like really effective and really simple to integrate into really all of the classes. So as a teacher, it might seem daunting to take this kit and do all the coding, but the instructions were all wonderful on the site. And I'm a techie person, but something new requires, you know, a walkthrough. And I was able to walk through all the pictures and all of the stuff. So by the time I met with kids, I seemed like I knew exactly what I was doing. I was just like 24 hours ahead of them. That's like really, that's all you have to be as a teacher sometimes, just one day ahead. So that's like one example of using electronics into, really it was an earth science class is essentially what it was. And so again, you might not think of that directly in an earth science project, but there are a lot of things out there when it comes to just gathering data that you can build through electronics.
Did you find that the students were, like just to sum up here, you find that the students were more engaged as a result because they actually got to hands-on build it and gather this data themselves?
Absolutely. Kids, the challenge I had for the kids was converting from Celsius to Fahrenheit. And so I was like, if you can figure out how to code that, we'll use your code for when we run all of our experiments. And so I had multiple kids tell me they spent hours at home researching and figuring out how to do the conversions in the code to make it work. These were 8th graders who spent time at home exploring code on their own for a science lesson that wasn't being graded. That is like the definition of engagement. when you're looking for kids that are totally into something, and it wasn't for a grade, it wasn't for any type of assessment. It was, I want to do this. This is interesting. I'm going to explore on my own time to make it happen. So for me, it was a great way to start the year, and it also really got the teacher like, oh, okay. So if you can find that one project, that one integration, that can lead to so many more collaborations throughout the year.
I know that I am one, despite I loved math and science growing up, nobody could make me sit there and like read the textbook on my own to research this kind of thing. But a project like that, yeah, I probably would have been doing the same kind of thing. So that's awesome that you were able to get the students that kind of engaged in the lesson. So how would you said this was for 8th graders. So how would you expand this to other science lessons? Like just using the climate kit as an example, how could you improve the data collection or make it more difficult? What other things would you look at with that set of tools among the different grade levels?
So you, with the whole kit, you can do wind speed, you have general humidity. So as you look at the different grades, I would think of like 6th grade where you would be able to do basic, even lower than 6th grade, basic temperature readings and more about the scientific process. Again, the hypothesis, testing your hypotheses and going around. So the fact that the microbit is attached to a portable battery allows you to travel throughout the entire school, or anywhere, is really interesting because then again, you can have those conversations of why is the temperature colder by the door as opposed to by the back of the room versus by the windows and by the heating vents? How does that, higher versus lower in the room? Like you can really start to have kids explore the space and see that. And you talk about humidity and, in Michigan, we've got all 4 seasons on any given day. So to have something like that to say, as a teacher to know that it's going to rain, and to not tell the kids, but have that microbit and have kids look at humidity and have discussions in regards to what is this going to look like? Why do you think that is? Or, the temperature and how that impacts whether you're going to get rain versus snow versus sleet. I think what's nice about it is that it is very flexible no matter what grade you are, because if it's just basic temperature readings, that's perfect. But like in 8th grade, we had kids complex coding conversions from Celsius to Fahrenheit and looking at humidity. And if you wanted to add wind speed and possible wind speed's connection to temperature, because we talk about wind chill factor, where it's 20 degrees, but it actually feels like -5 degrees because of the wind chill. So to have kids measure wind speed and do the conversion in regard to temperature can really take it to another level. And from there, you're looking at high school, there are moisture sensors that go with the kit as well. So you can have kids placing things in the ground on top of wind temperature, like how far deep can does the temperature change in the ground? So I mean, there's just so many different avenues to go for this. For just one kit. So for me, one of the things that you try to do as you're running a makerspace, you're running a technology budget, is that you want to get the most bang for your buck because you're limited in your funds. And so one kit like this offers so many different extensions in so many different areas. So for me, that's what made it so successful, is that this is something that can be used not just every year, but so many different classes across so many different grade levels.
Which is really neat to see from one kit like that. How do you get the students to think in a scientific way, both trying to discover things? Like how did you get the kids to, or how would you get kids to, say, measure the temperature by the door to see if it is colder or warmer? Do you just give them the kits and do they kind of figure that out on their own? Or do you say, hey, why don't you measure around the room and kind of prompt that?
So, this is where the teachers sort of come in big time, and the groundwork that they lay in regards to the scientific method and what does it mean to be a scientist and what are those steps. And so it was very easy to go in because the teacher would just say, okay, what's step 1 when we want to figure something out? And that's where the kids just start taking their guesses. And they go, okay. Then you ask the question like, well, do you think that's the same everywhere? And then the kids will start to go, ooh, you're right. It's warmer inside than it is outside. So that doesn't necessarily mean. So it's about questions, right? That's a Socratic method of just asking the right questions and helping the kids sort of lead to where they need to go. So for me, my job is to sort of like be an assistant in those classes. I provide the tools and help guide them when they get stuck. And the science teachers, with all their great training and expertise, are the ones that do a wonderful job guiding the kids in the direction they want them to go. And I think with any classroom teacher, you know the right questions to ask that will spark the creativity or imagination. And you know the right students who may be nudged a little bit to speak up, who has a really good idea. So really I rely on them, but it's just asking the right questions and listening and seeing where they're going and just prodding a little bit this way, a little bit that way to get the kids to explore maybe different ideas than the one that was first in their mind.
Right, so then once you have them guessing and coming up with these basically hypotheses, what are the next steps to move the students along to the hypothesis testing as part of the scientific method?
We start to just collect the information from the kids about the different things that we can do to test their ideas. And so if a kid says, well, I think it's always colder by the door as opposed to the people that sit in the back of the room, and say, oh, okay, so how do we test that? Like, how do we prove what you're guessing? Like, well, we just take the temperature by the door, we take the temperature in the back of the room. I go, okay, is the door open or closed? Oh, well, open. Well, we should do both, right? We have to do both. I'm like, you're right. Like, should the windows being open or closed, does that matter? Oh, well, yeah, if the windows are open, that could be. So it's just asking those questions. And so having them realize, oh, we need to test this, we need to test this, we need to test this. And then some kids shout, the ceiling fans. If the ceiling fans are on, maybe that's something. I go, oh, okay, ceiling fans on. And then even holding the microbit, a kid said, oh, if you're holding it with your hands, like you're hot, does that impact it? I go, that's a good question. I go, I don't know, maybe so we shouldn't hold it. Like, we should just set it down somewhere. No one breathe on it. No one breathe on it. Like, just listening to the kids, like, sort of go through this information, go through this idea of like how that impacts it is really interesting. So yeah, it's just, poking those questions and just saying, well, how do we test that? Like, what tools do we have available to us that can give us that information? And so as the kids start to explore those tools more thoroughly, they'll start to see what possibilities are out there to test different hypotheses.
So even as you're going through this process of trying to isolate your variables, you're finding that like the back of the room kids who are normally not engaged with class will come forward and start to be engaged if you kind of prod them a little bit?
Yeah, absolutely, because we are learners that like to move. Most of us, there are plenty of studies out there that show that the movement, physical movement, aids in learning. And so getting kids up and moving and walking around with a temperature sensor, a thermometer, and having them take this information and write it down and then discuss it. They're actively engaging in the learning process as opposed to sitting and watching a YouTube video alone or just reading something from a worksheet alone. Those things, can be helpful to reinforce ideas, I think. But to actually engage in that learning process, to walk around your school, to go to the principal's office and take a temperature and say, your room's warmer than everyone else's room. Why is that? Just it's to have fun and to see those things, and, going to a larger room versus a smaller room. And a kid saying, I wonder, the cafeteria always feels warm during lunch. Why do you think that is? And so you start to talk about body heat and, large rooms. And it's just fun because sometimes it takes something really small to spark a huge amount of questions and, scientific exploration. And again, it's natural in kids. The kids want to know about their surroundings. They want to know why things are the way they are. And so I think especially in lower school, our job is to keep stoking that flame of curiosity. And I think there are a lot of tools out there that can help support that are far more interactive than a textbook.
So what other skills do you think can be developed through these types of hands-on project-based learning that you're seeing here, specifically in science lessons?
Well, it's collaboration. That's huge. One of the things that I think all the science teachers watching can know is that there aren't enough supplies for every single kid to do the experiment all on their own, right? There are just some experiments that need to be done as a group. And part of that is collaboration. You need to be able to trust your partners to do the parts of the project that they're supposed to do, that they're adding the right amount of chemical to this. So I think collaboration is a big one. And I'm very lucky at my school, University Liggett School, is really about community, and it's about this collaborative effort that we are all in this together. Learning isn't a competition. It's about being together as a community and helping each other up, as opposed to trying to knock each other down. So I think when you look at science, you see those collaborative efforts with projects, which is really, science is project-based learning. And you know, there are plenty of science teachers out there that heard about project-based learning and go, that's literally what we do every day in class. And that's great. And I think you want to continue that. So you look at collaboration, you definitely want to look at to a degree, the design process. The kids in 6th grade built their heat keeper boxes. It's kind of a standard. I remember having that in middle school, where you design the box that's going to keep the beaker of water warmest by the end of like the allotted time period. So to watch kids go through the process of designing things and finding out what's a good insulator versus what's not. Again, these were solo projects, but that design process is a part of the scientific ideal that you're looking to install in kids, where it doesn't matter if it's an English class, a social studies class, a science class, designing something from idea to the end, I think is an important skill because it helps organize thoughts. And whenever you can help kids learn how to organize ideas, organize thoughts, that's a skill that helps you as an adult.
That reminds me of the egg drop we did. I think I was in 10th, 11th grade. We did the classic egg drop, design a container, we drop it from the back of the bleachers. Yep. They go down, and whoever egg survives, they win the egg or whatever it was. So I think that kind of goes towards more of the competition side, despite the fact that it is a design process. I had a lot of fun doing that one. My biggest concern is that we only did that one once. You had one shot to design a thing to drop an egg. I suppose I could have gone home and like dropped a bunch of eggs, but most people were, let's build a thing, put an egg in it, bring it the next day and drop it, and oh look, Susie's egg survived, therefore that design was best, and end of the lecture, right, or end of the lesson. Do you find that it's better to do something like that, where it's like everyone design a bridge or design the thing to try to keep the beaker of water warmest once, and you kind of learn off of each other, or do you do multiple iterations and you're teaching the design cycle of, you know what, try this, let's try a different material, and kind of foster that rather than assume the students will figure it out on their own?
The scope of the project is the really determiner of that. Like an egg drop is usually something really small that you could iterate multiple times. And I did the egg drop as well. And I was a big milk carton marshmallow guy. My marshmallows, that's what I used. But they had to be fresh marshmallows, as I learned, because they become stale and become hard. So you have to pack it right away with fresh marshmallows, and then the egg, and then more marshmallows to keep it alive. See, and that's what I learned after the first drop. After I packed it the day before, and all the marshmallows were hard and crunchy, it was not good. So that's something like small, or the bridge one, right? How much weight can you build on the bridge there? You can iterate very well. Larger ones like the heat keeper boxes, those can be tougher because those are like larger projects that might already take an extended period of time. And that's where you might look at what others did that were more successful and sort of share that information so that if a kid wanted to redesign, they could. But for any project, I think it's really important to give kids that opportunity to take what they've learned and apply it. Because that's what we're looking for in all classes, but in science is that it's not like you do an experiment, it doesn't work, and you go, oh, I know why, and then you just walk away. You take the why, and then you redo it to prove that it worked. Right? In science teachers, like I get it, like all teachers, you're crammed with more curriculum than you have time for. I totally get that, and that's super tough. So to try to build that in as best as you can is always really good, because it's one thing to do it, get it wrong, but know why it didn't work. It's another reason to take that why it didn't work, apply that knowledge, and to make it work, because that success is huge, and that application really shows a highest form of understanding of the material that you're covering. And so those moments can also turn kids on to science as opposed to off when they did something that didn't work, and they're like, well, that's it, didn't work, I'm done with science. That sounds silly, but some kids really react that way. When things don't work out, they just blame it on, well, I just don't get it. Giving them an opportunity to be successful after they failed can sometimes be a difference maker long term in the way that students regard science.
Going to the beaker heating example, can you provide a way that science teachers might, for example, shrink that project down to allow you to iterate it, maybe incorporate electronics to measure some type of heat, and then once the students are able to model it on a smaller scale, then blow it up to the bigger one? Is that a potential idea? Would you see that working in a classroom?
Yeah, there are plenty of again, temperature sensors out there that you could easily install into smaller designs. And a great example of sort of looking at scale modeling for sure is the one that shows clusters. They regularly would do things at a much smaller scale before they would even attempt the larger one, because the small scale was generally proof of concept. Well, this should work if we do it in this size for this ratio, so that when we build a big one, we just have to do the math to figure that out so it works at a bigger level. So they did scale modeling all the time, and I think that's a really great approach. When you have things like 3D printers, you can do a lot of scale modeling for things at much smaller sizes, as opposed to building a gigantic piece of something, which can take weeks and weeks and weeks. Doing something scale modeled with a 3D printer is tremendously easier for a whole classroom and things like that. So whenever you can scale model anything, it's definitely good, because it still gives kids the basic science concepts that you're exploring without a lot of extra time spent on construction of things that may or may not even work.
Yeah, so they find out on a much smaller scale and then iterate through it, ideally. And then, do you still recommend building the bigger model to show that connection in the classroom? Let's say we do the smaller scale heat transfer one, right? Do you say, okay, the students learned about X, Y, Z as far as heat transfer into the scale model, and then you say, let's build the bigger one? And is that you incorporate everyone or still keep those groups? What do you think works better in the classroom?
I think every teacher knows their classroom best. You'll find that in some where you're like, I've got a really motivated group, I'm going to give them all an opportunity to now take what we learned from the scale model and build their own with their own little flashes of flair. Or you might look at your class and say, you know what, this is a really good large collaborative group. So what we're going to do is we're going to do 2 or 3, and then we'll break the group into 2, half or thirds. So like any teacher out there, your classroom is yours to understand the best. And so for me, I've had English classes where it's been one big group project because the class is just in tune and click. Man, those kids could do anything together. And then I had some classes where it's like a lot of individual projects. I just had a lot of solo people, and it worked best for them to sit and do things on their own and then share class. So it really is up to the teacher based on the makeup of your class, which varies from class to class, which can also be true for any year, where first period is a great collaborative group, and then the second period is a lot of individual people. So I think trusting teachers to be the experts of their class is really the best way to approach any of those type of tweaks to projects like that.
Right, that's some pretty good advice. I never thought about that, like letting the teachers have their own domain and really reading the classroom. So I guess that's a really good skill too. What other maker type electronics have you used in the classroom to varying degrees of success? What do you like?
Yeah, so Makerspaces are super fun. Just even for me as an adult, I love making Makerspaces. So one fun project out of a 6th grade math class, the students were working on an XY coordinate unit, learning about plotting points on the XY coordinate plane. And so the teacher and another technology coordinator in the lower school, my friend Mike Manvinsky, worked with the math teacher to create a scratch-based arcade game where the kids would learn about XY coordinates by moving characters around on the XY plane. And so Erin Montaigne, the math teacher, wasn't super comfortable with Scratch. She's like, I really don't know, but if you guys say we can do it, I'll learn it, you learn it, and the kids will learn it. And we all dove in, and over the course of a couple of months, kids were spending some time in class writing code to make their arcade games, to move their sprites around the XY plane. And then the next level of that for the kids that really wanted to go one step further was to use Makerspaces to create controllers that they could control the games that they had created. So you look at adding electronics, whether it's code-based, web-based Scratch, whether it's a Makey to make a controller for their arcade game. I learned about XY coordinates with graph paper in high school, and maybe middle school. I mean, that was it. You had it, right?
Yeah.
You had the graph paper, and you're like counting each little box to make sure, like, this is 1, 2, and you're like, this is like terrifying. And, you know, I had kids be able to explain, oh, a negative X will put it over here, a negative Y will put it over here, and a positive X, negative Y goes over here. Like, these are 6th graders off the top of their head because they were able to apply, you know, which was traditionally a very static type of lesson, to a very interactive piece that was meaningful to them because it was their game. Like, I created this, I coded this, I know where things are in the XY plane. So when the code wasn't working, when something was going up instead of down, they go, oh, that's negative, positive. I must have forgot. And for them to switch that and know that is insane. But again, that's where you have an entire group of students engaged in something that was really not an engaging, you know, learning process before, at least, you know, not the way that I learned it. So to have an entire group of 6th graders in like 3 different classes engaging in this and understanding it, and then begging to continue to work on the games, you know, we ended up saying it turned to some degree into a computer science class for a chunk of time instead of just a math class. Which is good, and it definitely has its downside because you still have to cover a lot of math, and then it just turned into, you know, helping kids code a game. But the coding of the game started from the base lesson of learning XY coordinates. So that turned out really well, and using a Makey to do that is actually a very simple thing. There are definitely kits that you can get that come with all the wires, and the Makey kit. It's really great to plug things in, and kids using Play-Doh to create controllers, and conductive metal tape that you can buy to act as the ground. It was really cool to see the kids just sort of explore what that could look like, all because they got sort of going with an XY coordinate unit in a 6th grade math class.
So how did you find that bringing in the Makeys helped elevate that to the next level? Because you can control Scratch through your keyboard, your mouse, whatever you have,
yeah.
But bringing in that hardware, what did you find did for the students? How did that help them?
It was sort of like the extra bonus to finishing your game is to then design your own controller. So with us, with the CNC machine and the laser cutter, you're able to cut cardboard or wood or laser it however you want. So for the kids, they know, ooh, if I finish my game and I get it tested and approved by 3 different people, I can get into the controller design. Like, how awesome is that? So again, to see the kids think about the design process in regards to, well, what does a video game controller look like? What should they look like? How many buttons do you need? Like, what are you going to use for buttons? Like, why will that work? You know, so, and for me, it was fun because I got to make my own template for that, which was super fun to do, to build my own Makey controller. But I just used cardboard, brass brads for the directions and the A/B buttons, and then the conductive tape at the bottom that acted as the ground. And I just cut it into 5.5 or 5 by 2.5 dimensions, which is like the perfect sort of like Nintendo controller size. But then we started talking about proportions in class. So well, why can't you just make it a square? Like, why can't a square controller work? And I go, oh, I don't know. That'd be kind of weird if you think about it. So then we had kids explaining how that would or would not work. And so how things fit in the hand. So we talk about ergonomics with kids. Like, it was just weird. Like it has to be comfortable. If you're going to hold something, it needs to be designed so it's comfortable to hold. And so a kid wanted to make a triangle as a controller. I just said, okay, let's cut that out of cardboard and see what that would look like. And, you know, the idea was fun or novel, but as he tried to hold a triangle controller, he's like, this doesn't work the way I thought it would. But again, right, that's that design process of taking an idea and then actually having a prototype of it and going, oh, this is the worst idea ever. And then going back and going, you know, people made a good choice with rectangles. Rectangles make good controllers. Yes, they do. So it's like things like that where it's a 6th grade class, you're talking about XY coordinates, but then you start talking about geometry, you're talking about like ergonomics with like what fits well in your hand. And like that, again, that design process is, you know, all throughout. And that's what's really nice is that, you know, kids, again, are learning how to think, learning how to plan, learning how to experiment. And I think those are skills that you need as an adult for your whole life. No matter what your job is, you need to be prepared to plan and experiment and try new things.
I'm guessing that during that class, nobody raised their hand and said, how will we use this in real life? Because that was like the most common question in math class ever for me.
Yes.
How will I use geometry? Well, controllers, ergonomics, kind of good to know geometry for that one.
Yeah, well, I'd say as an adult, if you own a house, you're in a house, geometry you're going to need. You're like carpet, you're going to get paint, you're going to do square foot. Like geometry is like the one area where I could actually, as an adult, go, I wish I paid a little bit more attention. Because that's something that I could be like, oh. But again, if I would have been taught geometry in the sense of, hey guys, here's a house. Here are the things that you need to do. Like here are like the different dimensions of your, like, I would have like been a little bit more engaged instead of just looking at a bunch of rectangles, triangles, and squares and, you know, things like that, or algebra where, you know, my philosophy is if I'm ever in a situation where there are 3 variables, I'm walking away. Like whatever is going on is far beyond my needs. And I don't know 3 things that are going on in this situation. I am in way over my head. But no, there were no kids. Like they were just like, this is awesome. And as teachers, you know, one of the things we have to do is sort of play the game of tricking kids into learning by doing fun activities. And so we easily could have taught everything that they needed to know about XY coordinates, pluses and negatives through very static instruction. Totally possible. That's how we learn, how people have learned for decades. But if you can tell kids, hey, we're going to make video games in math class, and kids are like, I'm on board. Everyone's on board. As opposed to the static way where maybe 40% would have been on board, and the other 70% would have been like, I'm going to do this because I have to do this because it's a grade, so let's just get this over with. But to see kids actively engaged, kids that would be considered students who struggle with math, to explore it, and for them, if they were to be assessed, would say, oh, I know where this is because in my game, my sprite moved up and down this way, so this question's asking me to do this. You still there?
Yeah, uh-oh, did I lose you? I can hear you.
Oh, yeah, the picture went away.
Yeah, hold on one second.
There you go. We got shut off. I'm back. I can see me. There you are. Hi.
We just switched, that's all.
Yeah, our conversation was so good we broke the live stream, which it happens when you're having this much fun.
I've had it happen before,
so yeah.
You know, you just have to go with it.
Right? So when kids are engaged, and you're trying to engage as many kids as you can in any type of classroom. So something like this engaged the entire class and had kids coming to me after school saying, will you help me with my Scratch game? Can you dive deeper into this? I had a girl who built 5 levels into her game. You had to just do one, just one little simple game. She built 5 levels into it and had me play it because she was having trouble with level 5, but the only way you could explore level 5 is if you played through the 4 levels. I had trouble getting through her 4 levels to get to level 5 to see why it wasn't working right. And so she goes, oh, well, there's a cheat here. If you move your character here on each of these levels, it could actually get you through it faster. I'm like, why didn't you tell me that? She goes, well, I forgot. And I go, well, why did you build it in? Well, I didn't want to have to like play through all 4 levels to get to that. She's like, that's what you do. You build those things in so you don't have to do like that. But that took planning. That took like an amazing amount of like thought process of, oh, I'll program it so if I stand right here, I'll never get hit so that I can beat the levels. It's like she essentially built a back door into her code so that an engineer can get in and see what works. So like that's nuts. That's a 6th grader who said, oh, I did this, this, and this, and this. And I never would have thought of that. I just wouldn't have occurred to me to sort of code in a back door so I can skip through the levels really quickly to assess what needs to be assessed. So like just the things like that show me the value and show teachers the value. So like when I share that story and with just the teachers in my own building, you know, like this is an example of a student that you might not necessarily view as an always engaged student, engaging in something and then dedicating their free time and then going home and telling their parents about it and having them email, so my daughter says she's a coder now, like that's okay, like what does that mean? And she says she wants to take coding classes, and that's phenomenal. So when you look at, especially when you try to look at increasing the number of young ladies involved in STEM or STEAM programming, to see her coming so excited about creating this game and you know, exploring code, like those are things that you want to see, because it's around this time, especially in middle school, where you'll start to see the genders start to separate in terms of STEM, STEAM areas. The numbers start to drop off right before you get into high school. And to see a young lady be super pumped about it and point her towards other amazing women coders and scientists and say, hey, here's some people that do this. Like, look at what they can create, look at what they do. And for her to go, oh, that's awesome. Like, I could totally do that. For me, that's really important because I think those are areas where we need to definitely diversify the people that are involved in STEM and STEAM fields.
Yeah, I would love to see that too. When I was in school, I think there was maybe 20% engineers were women. So I am happy to see more engagement, especially at the younger levels, and trying to keep them through that. I understand you've done some stuff with LilyPad. Have you had any success trying to get people, maybe women or others who have not identified with STEM, to come over and be more interested in science because they've played with this device?
Yeah, LilyPad's fun because when you're playing with small LEDs and sewables and conductive thread, it's kind of like magic to some degree. When kids ask me how things work, my first answer is magic. There's a lot of science behind it, but it's just way easier to say magic. The fact that I can click this button and all these lights will turn on, and I wrote the code to do that, like that's crazy. Again, I'm new to the world of like coding, maybe 5 years now. It's something I've really committed to learning, and it still blows my mind when I can make a light go on or off. Like I made that happen. And so to see a student though have that same like revelation, like, whoa, it turned on because I told it to. This is amazing. And they start to explore. And one of the things I want to do is get more LilyPads so that we can start to see more permanent builds from students. Like right now, I think I have 2, and so it's sort of like a learning process for them just to see what's possible with it, and then maybe asking mom and dad for their birthday for their own LilyPad kit so they can start to really dive in and design their own jewelry or clothing or things like that. So definitely I see girls lean more towards it for sure. But even some guys are like, oh, I could totally put this in the back of my jacket while I'm skateboarding, and I can put the lights on, and I could make like turn signals. I'm like, that is insane, but okay. I'm like, that's feasible, because they're like, yeah, because the thread like will carry it all the way to wherever it is. So I would put just one on my left and then one on my right hand. So I would just have to like click my thumb or something, and then the light would turn on, so people would see me turning at night. I'm like, okay, like that's a good theory. I'm like, again, let's test that out. So yeah, LilyPads have been like a nice addition to the makerspace in the textile area for sure. So the patches of fabric, and I recently cleaned up my closet and donated all of these old ties I don't wear anymore. So kids are cutting up ties and thinking about adding LEDs and things like that. So LilyPad has been a really nice addition. I think it's a very simple entryway into coding, LEDs, and things like that. So if you have people that are really hesitant, a LilyPad is a very easy entryway into that, just because it's very simple to construct, and you're just talking about thread. So you're just sort of tying things together and adding LEDs. So, and with conductive tape, it also works together really, really well. So for those out there that are looking for an easy entryway, just to say, hey, give this a go, LilyPad is a really wonderful tool to explore. So maybe just get the conversation started.
Yeah, so thanks for sharing that, and that's a good to know that it's not just you get women involved, but you also get guys involved in knowing like, oh, it's not just electronics and programming mainly, but like I can integrate this my clothing and do things that I want. So it kind of acts as this like level playing field for both stereotypical genders wanting to do one thing versus the other, and says, hey, you can kind of do both with this. And it's great to hear that you have students of all genders and however they identify coming in and wanting to play with these electronics and testing their hypotheses. I think we've got about 5 minutes here. If you have any more questions for us, please ask us on YouTube. Looks like we've got one here. This one has, how do you? Oh, okay, sorry. I have somebody here sending me notes about questions from YouTube. So I'm not like magically downloading the YouTube questions in my brain, like I'm getting them slid to me, so I've got notes here. So the question is, how do you promote your makerspace?
Oh, great question out there. So it works sort of on its own. And really, word of mouth is the best way for the makerspace to spread. So one of the things that I've implemented in my space is a badging system. So I really think it's important to recognize the skills that students earn outside of the traditional curriculum. So kids can come in and earn their badges for 3D design, 3D printing, Python coding, Raspberry Pi, and things like that. So I created badges, and I created like these benchmarks. So if they achieve these benchmarks, accomplish these tasks, they get a badge. And at first it was just gonna be digital badges, but kids really wanted physical badges as well. So I printed off the badges on sticker paper, cut them out, and then the kids put them on their own devices. And then they would walk around with their laptop, their iPad or whatever with these stickers, and kids would go, where did you get that? Why did you get that? So it became like this own like sort of advertising, which was really crazy. But really kids word of mouth, you know, in middle school, if kids think something awesome, they'll tell everyone else, this is awesome. So the kids building the cardboard fort in the makerspace right now, and it's just been word of mouth of kids like, can I come and work in the space? Can I help on the fort? I go, it's not my fort. You're welcome to come in here and ask them if you can build, but you're all welcome. So it's been word of mouth, and that's what's exciting. And it's, for me, our middle school 6th, 7th, and 8th, it's been more 6th graders than everyone else because it's new. Like they've never been to middle school before, so they just assume the makerspace has just always been there when I'm brand new too, and the makerspace is brand new. So, you know, the 7th and 8th graders are less active, but that's just because it's really new to them in the space. Some of the 8th graders are really starting to explore it some more, but the 6th graders are really embraced it as like, this is awesome, this space is cool, and I'm excited because I've got them for 2 more years. So that'll continue to grow. So really advertising it with talking with kids, finding out what they want. Also sending emails home, asking parents for broken electronics or cardboard boxes or boxes of Legos that are unused anymore. I mean, these are things that help supply a makerspace. And so just sharing with them, and then the parents know about it, they'll ask their kids like, why aren't you going down to the makerspace, or why aren't you doing that? And I've had parents push their kids to try it out, and the kids go, this is amazing, or why didn't I have this? Or I have high school kids that come by and go, this is not fair, I didn't have this in middle school. So the advertising sort of does it itself as long as you are open and inclusive and give every student a chance to make. A makerspace will sell itself for sure.
Nice. Okay, I got to ask about your shirt. You're wearing a Raspberry Pi shirt. Yeah, da da da. Like you do the Superman thing, and just like tear open the Raspberry Pi logo right there. So you're a Raspberry Pi certified educator. How does that help you, and what did you have to do to get that?
So this was, 2 years ago, they held their first Pi Academy in the United States, and Pi Academy is a free 2-day workshop run by the Raspberry Pi Foundation to give you like in-depth training on how Raspberry Pi can be used in education, and how Python, you're focused on Python and physical computing. So I heard they were coming, and I didn't know anything about Raspberry Pi. I didn't know anything about coding, but I had students that were working on projects that started to include Raspberry Pi in coding. So I said, I have to learn about this. Like, if my kids are gonna be using it, I wanna know about it. So I went, and I was blown away by, really was like the best professional development I've ever had. And I learned about coding. I learned about connecting like Twitter to Python code to send tweets through the pushing of a button, through taking pictures, developing my own projects. I became obsessed with Raspberry Pi, and as a certified educator, I've been very lucky now to work at Pi Academies and help train other teachers. So it's one of the things that I've been able to do is give back, and I've been lucky enough to go out to Cambridge in the UK and visit the Raspberry Pi people out there. And just learn so much about it, and to write for their magazine, Hello World, which is fabulously filled with great stuff. It's free, it's online. It's called Hello World. You can download the PDF. It's filled with great educational stuff on using Raspberry Pi. But I'm surrounded right now in my basement with like 4 or 5 Raspberry Pi projects that are doing something or another. And it's great because it's low cost, $35 for a Raspberry Pi. allows kids to really dive in and create and explore. And if they make a mistake or something breaks, if you really crash the code, the SD card that's running it is only like $10. And if it somehow, yeah, right, pop a new one in, get to work. If you somehow destroy the board itself, which takes a considerable amount of effort, it's a $35 replacement fee as opposed to, a full laptop or desktop or something like that. So yeah, I'm an advocate for them. Raspberry Pi believes that every student should have an opportunity to explore computer science. And I never thought I would say this as an English teacher, but that's my mission too now, man. I want every kid to explore this because as a dyslexic English teacher, the fact that I can code and the things that I can make with it really, really makes me believe that anyone can and should at least give it a go, because it opens up a whole new world. And I can now look at our surroundings and look at electronics in just a different way. Like I go, I know how that works, or I get that now, as opposed to just taking those things for granted. So having kids see that at a younger age opens them up to a world of possibility as they start to explore careers and the things that they want to learn.
Awesome. All right. I think I have time for one more question here. So how can teachers in other fields or community members help get kids excited about STEM? This is from the YouTube.
Yeah. So if you're in other content areas, I think one of the things you should do is look at collaborating with those other content areas. If you're a social studies teacher, let's say you connect with a science teacher and you talk about great historic scientific discoveries and you want to recreate some of those discoveries. And so you have social studies teacher, history teachers exploring, the history behind these things. And then you're coordinating with a science teacher to explore, recreating these old experiments that gave us something that's so important. So sometimes it's cross-pollination of content areas that can go really, really far. And working with an English class to work the paper on it, to working with the math class to figure out the math aspects of it if that's needed. I think you can combine a lot of those things. In regards to community, we need to be comfortable reaching out to parents and saying, hey, I heard that you're an engineer. Is that true? Or your son says that your brother is an engineer. Is there any chance they could come in and talk about what they're working on? I heard they were involved in the new, AI programming of the Ford Focus or whatever. And, can he come in and talk about that? And I think bringing those people in, and I think utilizing social media, reaching out to scientists on Twitter and authors on Twitter. Like, these are people that are out there that it used to be impossible to get someone to come and talk to your class. Just the flights and hotels and the money. You'll find so many people that are willing to jump on a video chat and talk to kids because they see the value in, wow, if I can talk to 40 kids and show them why planetary science is so really important. That's one of my nerdy things I do on my Twitter account is I follow a lot of planetary scientists. I don't know why. I just am really fascinated by the things that they share. And this is super cool to me. So I'll interact with them once in a while. And again, as a high school English teacher, I never thought that would be a thing, but I've always loved the sciences. So, reaching out to those people and say, hey, would you talk to my class for like 30 minutes about, the meteor shower that's coming up? And, to be able to say, yeah, cool, like no problem. That's awesome. Like, that's like amazing because, technology has now offered us the opportunity to connect with people all over the world. And I think as a teacher, it would be almost malpractice not to explore ways to connect kids to these other people from all over the world and different cultures and things like that, because that is where we are as a world now. We are a global learning effort. And if we want kids to learn and understand our community as a whole, we need to be making those connections as best as we can. So if we want to, really the problems that we face as a world, whether it's climate change and things like that, that's going to be a worldwide problem that needs to be explored. So if you can connect with other people outside of just your classroom and your textbook to explore those ideas and how they can be solved or addressed, I think is a great way to keep encouraging kids in the STEM and STEAM fields, because it's going to be those fields that help solve some of the biggest problems that we're facing today and down the line.
Awesome. Well, thank you so much for joining us, Nick. This has been absolutely wonderful. And sharing your expertise with us and then everybody else watching. Final question for you. If people who watch this maybe in the future want to reach out to you, I know you have a site, thenerdyteacher.com. Am I getting my URL correct on that one? How else can they reach out to you? Do you have a Twitter account that people can reach you at?
Yeah, so if you're interested in the Makerspaces and those type of things moving forward, you can reach me on Twitter at the Nerdy Teacher. And my Instagram, I share so many of the student projects and things that I'm working on in the maker world, and an occasional really good meal too, if that's your thing, at the Nerdy Teacher on Instagram as well. And then of course, if you really want to dive into Makerspaces some more, you can totally pick up my book. You can find that online. If you are a super huge nerd like me, this is just a book that is very plain spoken, filled with nerdy references, to get you started on exploring what making looks like in your school for your students.
I love it. Well, thanks so much, Nick. And I had a great time talking to you, and I hope this has helped everybody out there. So have a good day.
Yeah, bye. Thanks for having me in. Take care, everyone. If you need anything, reach out.
Yeah.